The next mathematical concept we'll be talking about is the concept of eigenvalues and eigenfunctions. So now that we've talked about operators, one type of equation that we often need to solve in quantum mechanics looks something like this. We have an operator operating on some function. We'll give it the symbol phi, right? So operator operating on some function. This will be often a wave function. We'll get into what that is. Will be equal to some constant, we'll represent as lowercase a here, times the same function again. So we operate on the function and we get back a constant times that function. This type of problem like this is known as an eigenvalue problem. And let's define some terminology here. So phi of x, this function that satisfies this type of equation, this is known as an eigenfunction. And if I'm not mistaken, eigen is a German word that means self. So it's a function that returns itself after you do this operator on it. So it's called an eigenfunction of the a operator, whatever that operator is. And a, the constant that we get, is known as an eigenvalue of the operator a. And so this terminology is a little confusing, maybe not confusing, but maybe not familiar. If you've happened to have taken linear algebra, which is not a required class for this course, you probably have seen this idea of eigenvalues and eigenfunctions before. But if you haven't seen it before, that's fine. That's why we're introducing it now. And so let's, as with anything in quantum mechanics or anything else, it really helps to see examples and how do we apply this. So let's look at a simple example. One operator that we will come up against that we'll see is this momentum operator in the x direction. So p of x. And we'll see that operators can take many different forms. The p of x operator, so momentum in the x direction, the operator is negative I h bar, first derivative with respect to x. And that is the definition of the operator. This represents momentum in quantum mechanics. And an eigenfunction of this operator is this function. We won't show how we get this. This is just, take it as an example. One of the eigenfunctions is e to the ikx. So let's go ahead and go through this eigenvalue equation and show that this really is an eigenfunction of the momentum operator. All right, and so if we take our p of x times our phi of x, we should get a constant in our same function back. All right, so let's go ahead and do that. Negative I h bar, first derivative with respect to x of e to the ikx. Okay, so we take the derivative of an exponential is, these constants up here times that exponential again. So we'll get negative I h bar times I times k times e to the ikx. All right, and so then we end up with a negative I squared h bar times k e to the ikx. And I squared is equal to negative 1. So overall, we end up with positive h bar times k e to the ikx. And we see we do have our original function right here. This is our phi of x. And now we have just some constants here. This is our eigenvalue. So this is an example of an eigenvalue equation for the momentum operator. And so we would say that the eigenvalue of this is h bar k, the eigenvalue of the momentum operator, and the eigenfunction is e to the ikx. So this is an example of an eigenvalue equation. And we'll see these show up a lot in quantum mechanics.